Hi students, in this session I am going to start a fresh chapter, that is analysis of linear systems. Analysis of linear systems. In this, the first topic is introduction. Introduction about the unit analysis of linear systems. So in the introduction I will explain you what a system is, because we are going to analyze a linear system. To analyze a linear system, first of all we have to know what a system is, and then we can go for linear system, and then you go for analysis. So for that, in the introduction, first I am going to explain you about the system, what a system means. Here we all know the definition for system, because I explained you the concept of system at the beginning of this subject. At the beginning, that is in the first unit itself, I explained you what a system is and what are the classifications of systems. In that we have linear system, a time variant system, time invariant system. So I explained everything clearly at the beginning of the subject, that is at the first unit. In the first unit I explained you clearly about the classification of systems, so you have to recollect all those things. Okay, so the same concepts I have to explain here also. So here I am starting with a system. What is the definition of system? Simply, a system is defined as an entity. A system is defined as an entity that acts on an input signal, and transforms it into an output signal. Simply, a system is defined as an entity, that acts on an input signal. So here what system will do? The system will act on input signal and transforms that signal into an output signal. That means the system will take a signal as input and it goes for some processing, and it produces or generates another signal as output. So that is nothing but system. So here it will system take a signal as an input and generates another signal as an output. The total combination is nothing but a system. So simply, a system is defined as an entity that acts on an input signal, and transforms it into an output signal. Okay, in this system we have two most important attributes. The two most important attributes of a system are, first one linearity, and the second one time invariance. These two are the most important attributes, because in classification of system we have many number of classifications. Okay, a linear, time variant, a causal, a static. We have more number of classifications. So in that, the two most important attributes are linearity and time invariance. Based on the combination of these two, we have linear time invariant system and a linear time variant system. So based on the combination of these two important attributes, we have two important types of systems, that is linear time invariant system and linear time variant system. So first we have to know what a linear time invariant system is, Okay, a system which is both linear and time invariant. A system which is both linear and time invariant. Those system is nothing but a linear time invariant system. A system which is both linear and time invariant is called a linear time invariant system. Simply we call it as LTI system. And a system which is linear, but time variant system, which is a linear but time variant. That type of system is called as a linear time variant system. Simply we call it as LTV system. Okay, so a system which is linear but time variant, simply it is not time invariant. Not time invariant means it is time variant. So a system which is linear and time variant is called a linear time variant system. Okay, so we have to go for the analysis of these two. Mainly we will discuss about LTA systems. LTA systems. Okay, here the important point is the change of shape of a signal. The change of shape of a signal when it is transmitted through a system is nothing but distortion. The change of shape of a signal when it is transmitted through a system is nothing but distortion. So simply take a system. Take a system. Okay, for that you are given a signal as input. Signal as input. So the system will process the signal and it will produce another signal as output. Okay, while processing the signal, if at the output there is a change in the shape of the signal that I had generated, that I had given at the input, then that change in the signal at the output is nothing but distortion. So here I had given a signal like this. Okay, and the signal is processed, and if there is a change in the shape, there is a change in the shape of the signal that is transmitted through the system, then we call that as a distortion. But for perfect output we don't need the distortion, that is we require distortion less transmission. Okay, so here in the analysis of linear systems we will go through all these ones. That is, we will go through what a system is, and then we have to know what a linear system is, and we have to know what a time invariant system is, and we have to know what a time variant system is. So I have to discuss one by one clearly. First I will start with the system, and then I will go with the linear system, and then I will go to time invariant system and time variant system, and last I will go for the linear time invariant system and linear time variant system, that is LTI systems and LTV systems, one by one. So here in this unit we can discuss about the filter characteristics. We will discuss about filter characteristics, distortionless transmission, system bandwidth, signal bandwidth. All this concept will come in this unit. Now I will start with the system. You all know the definition of system. That is, a system is defined as a physical device. A system is defined as a physical device which generates an output or response for a given input. Which generates an output or a response for a given input. That means here output or response both are same. Okay, so technically we call that output as a response. Okay, now what the system will do? The system will generate a response or output for a given input. Now we go on to the linear system. So which system is called as a linear system? A system which satisfies both the principles of a superposition and a homogeneity is called a linear system. That is, if I want to say a system as a linear system, it has to satisfy two principles. The first one is superposition principle, and the next one is homogeneity principle, or simply they can say it has to satisfy additive property and homogeneity property. Then we can say that system is a linear system, if you want to say it in a simple manner. Okay, or you can say if a system satisfies the principle of superposition and the principle of homogeneity, then we can say that system is a linear system. Okay, here a superposition and homogeneity means the weighted sum of the inputs, is must and should be equal to the corresponding weighted sum of outputs. Weighted sum of input signals is must and should be equal to the corresponding weighted sum of the output signals. Okay, simple. Here we have to consider the weighted sum of inputs. Inputs means let us take two inputs as x1 of t and x2 of t. So I have to multiply those signals with the constants, then we get the weighted inputs. Let us take the signal is x1 of t. Signal is x1 of t. So weighted input means I have to multiply this with a constant. If I multiply it with a constant, a into x1 of t. I am considering another signal as x2 of t. Weighted input means I have to multiply with another constant b. So these are nothing but the weighted inputs. Here sum of the weighted inputs. Sum I have to add those two. So sum of the weighted inputs a into x1 of t plus b into x2 of t. Sum of the weighted inputs is equal to the corresponding weighted sum of the output signals. So corresponding, that means the x1 of t has to produce an output and x2 of t will produce an output. So see, if x1 of t produces an output y1 of t and x2 of t produces an output y2 of t, okay, then a corresponding weighted sum of outputs means here a is multiplied with x1 of t and x1 of t is producing an output y1 of t. So in output also the weighted output, first one is a into y1 of t. So a into y1 of t and x2 of t is multiplied with b. So here also the output of x2 of t is y2 of t, that will be multiplied with b, and if I add those two, that will become as weighted sum of output signals. Weighted sum of output signals, that is for the given system. If we give the input as a into x1 of t plus b into x2 of t, then the system has to produce an output like a into y1 of t plus b into y2 of t. Then I can say that system is a linear system. If you want to express this, we can say like weighted sum of inputs is equal to the corresponding weighted sum of outputs. Weighted sum of inputs must be equal to the corresponding weighted sum of outputs. Okay, simple for that. To explain this weighted sum concepts, I had taken two signals, x1 of t and x2 of t. First, x1 of t produces an output y1 of t and x2 of t produces an output y2 of t. Then the system is linear if a into x1 of t plus b into x2 of t, that is weighted sum of input, produces an output a into y1 of t plus b into y2 of t, that is weighted sum of output, corresponding weighted sum of outputs. So see here, inputs is a into x1 of t plus b into x2 of t and the output is a into y1 of t plus b into y2 of t. Here the weighted sum of inputs are producing a corresponding weighted sum of outputs. Then I can say the system is a linear system. Here a and b are nothing but constants. Here a and b are nothing but constants. So if you want to represent in an equation format, we have to write like this. T, that is transformed version of a into x1 of t plus b into x2 of t is equal to a into y1 of t plus b into y2 of t, nothing but transformed version. So if you want to write the relation between input and output, if x of t is producing an output y of t, if you want to write this in an equation format, how will you write? A transformed version of x of t is equal to y of t, because x of t is producing an output y of t. So x of t is transformed to y of t through the system. So I have to write transformed version of x of t is nothing but y of t. In the same way, here the input is a into x1 of t plus b into x2 of t. It is producing an output a into y1 of t plus b into y2 of t. So the transformed version of a into x1 of t plus b into x2 of t will produce an output a into y1 of t plus b into y2 of t. So this is a simple explanation about linear system. Okay. So next I will go on to the impulse response. Now we move on to the topic impulse response. Impulse response. The name itself tells us response is the output, and here impulse is nothing but the input. That means for a system, if we give unit impulse as input, it will generate an output. That output is nothing but the impulse response. That output is nothing but the impulse response. So the name gives the impulse response is nothing but the output of a system whenever you give unit impulse as input to that system. Simply it is the output of the system for which we give unit impulse as the input. If you want to represent it diagrammatically, see, we can represent like this. Here I have to take a system. I have to consider a system. For system, if we give input as unit impulse, that unit impulse is represented with del of t. If I give unit impulse, that is del of t, as input to the system, then the output produced by the system is nothing but the impulse response, because it is responding for the given impulse, hence it is called as impulse response, or it is producing an output for a given unit impulse as input. So the output of the system is nothing but the impulse response, and the impulse response is represented with h of t. We will represent the impulse response with h of t. Simple. So this is nothing but impulse response. So impulse response is the output of the system. Impulse response is the output of the system for a unit impulse input. Simply impulse response is the output of the system. For a unit impulse input. Whenever we give unit impulse as input to the system, the output produced by the system is nothing but the impulse response. Okay, and this unit impulse response is very important for understanding the system behavior. We need this unit impulse response. So it plays a major role. The unit impulse response plays a major role in understanding the concepts of system behavior, how the system is behaving. So that will be known by unit impulse response. Okay, let us consider if the input to the system is del of t. That is, generally we will consider the input as x of t and the output as y of t. So I am writing, if the input x of t is equal to del of t, that is, the input what we will give to the system is del of t, that is, the input x of t is nothing but the unit impulse. Then the output, generally we represent the output as y of t. Then the output y of t will be equal to impulse response, that will be represented with h of t. Whenever x of t is equal to del of t, at that time the y of t will be equal to h of t. That is, whenever the input to the system is unit impulse, then the output produced by the system is nothing but the impulse response h of t. Okay, now we all know the Fourier transform of this del of t is 1. I already proved it. Fourier transform of del of t, for the unit impulse the Fourier transform is 1. Okay, the Fourier transform of unit impulse signal is 1. In the same way, Laplace transform of unit impulse will also be equal to 1, L of. Okay, Laplace transform of del of t is also equal to 1. Okay, impulse response of the system can be found by finding the inverse Fourier transform of h of omega. In Newton, capital H of omega. So here I want to find the impulse response of the system. That impulse response of the system can be found simply by finding the inverse Fourier transform of h of omega. How can you write it mathematically? So h of t will be equal to inverse Fourier transform of h of omega. So h of t is the impulse response. So we can find the impulse response of the system by finding the inverse Fourier transform of h of omega. So the new term is h of omega. What is h of omega? So here h of omega is nothing but the transfer function of an LTI system. H of omega is the transfer function of an LTI system in frequency domain. LTI, linear time invariant system. Okay, h of omega is the transfer function of an LTI system in frequency domain. Hence, we written as omega. So, whenever there is omega, it is nothing but in frequency domain. Simply transfer function, that is in frequency domain, the output by input. Let us consider if the output is y of omega and the input is x of omega, then the transfer function is y of omega by x of omega. Impulse response of the system we can find simply by finding the inverse Fourier transform of h of omega. That is mathematically written as h of t equal to f inverse of h of omega. Here h of omega is the transfer function of an LTI system in frequency domain. In the same way, I can find the impulse response of the system. I can find the impulse response of the system by finding the inverse Laplace transform. Inverse Laplace transform of h of s. Inverse Laplace transform of h of s. That is simply the impulse response h of t equal to inverse Laplace transform L inverse. Inverse Laplace transform of h of s. Here h of s is the transfer function of an LTI system in S domain. In S domain, where h of omega is the transfer function of an LTI system in frequency domain. So this Fourier transform is for frequency domain and this Laplace transform is for S domain. We all know the Laplace transform is for S domain. So h of s is the transfer function of this LTI system in S domain. In S domain. So this is the explanation about impulse response. What is impulse response and what is the importance of impulse response and how can you find out that impulse response. So this is a small explanation about impulse response. Now we move on to the topic response of a linear system. So how a linear system will respond, that is if the given system is a linear system, then how the output will be for that linear system. There is nothing but the response of a linear system. Okay, simple. The response of the linear system, generally we will represent the response of the output with y of t. Hence I represent it as y of t. Here the response of the linear system y of t for any given input, we will represent the input with generally with x of t. So for any given input x of t can be obtained by simply convolving the input with the impulse response of the system. Convolving the input with the impulse response of the system. So I already told you that this impulse response will play a major role for understanding the behavior of the system. So here see the response, the output of the linear system y of t for any given input x of t can be obtained simply by convolving the input with the impulse response of the system. That is, here I am considering the input as x of t and we know the impulse response of the system is represented with h of t. This impulse response of the system is represented with h of t. Okay, so now I have to convolve this x of t with h of t. So x of t convolution h of t will give the response of the system, that is y of t. So simply y of t will be equal to x of t convolution h of t, or you can write y of t equal to h of t convolution x of t. So both are same. Okay. So the response of the linear system y of t for any given input x of t can be obtained by convolving the input with the impulse response of the system h of t. That is simply y of t equal to x of t convolution h of t. Here the convolution is represented with the star. So y of t equal to h of t star x of t or x of t star h of t. Okay. In this response of a linear system, we have 4 cases. In the 4 cases, a complete concept is around causal signal and causal system. So dependent on the concept of causal signal and causal system, we have four ways of representing this response of a linear system. The first one is if a non-causal signal is applied to a non-causal system. That is, the signal is non-causal and the system is also non-causal. For those, what will be the response of the system? For those, the response y of t will be equal to, so both are non-causal. Non-causal means, so when we say a signal is a non-causal, that means it has to exist for both negative and positive. For all, we will get, if we get a signal, then we can say that as a non-causal. Hence we have written integral minus infinity to infinity h of tau x of t minus tau d tau. So this is the formula for convolution of h of t convolution x of t. For this, the formula is integral minus infinity to infinity h of tau x of t minus tau. Or you can write like this also. Integral minus infinity x of tau h of t minus tau d tau. Why? Because h of t convolution x of t will be equal to x of t convolution h of t. Okay. So for a non-causal signal is applied to a non-causal system, then the response y of t will be equal to integral minus infinity h of tau x of t minus tau d tau equal, and that is same as integral minus infinity x of tau h of t minus tau. This is nothing but the formula of convolution. Here we have taken the non-causal signal and non-causal system. So for that, the limits are from minus infinity to infinity. Next, the second one is if a causal signal is applied to a non-causal system. Here the signal is causal, that is applied signal is causal. See, this is applied signal x of tau, that is causal. So when we say signal is causal, so we will say a signal is causal whenever the signal is 0 for t less than 0. That is, for negative values of t, there will be no signal. That means the signal has to exist only for positive value of t. That is, whenever t is greater than 0, then only the signal exists. Then we can say that signal as a causal signal. So if a causal signal is applied to a non-causal system, okay, so come here, the signal is x of t, input signal is x of t. So see, represent x of tau, because it is, while we are representing the formula for convolution, so we have to write x of tau into h of t minus tau d tau. Okay, so this will be causal, that is greater than 0. The t value should be greater than 0. So for that reason, we have to consider 0 to infinity. And see, causal signal is applied to a non-causal system. The system is non-causal. Hence, we had gone with minus infinity to t h of tau x of t minus tau d tau. Okay. So how to remember means simple. So remember this one. The signal is causal. The signal is causal means the causal signal is the one which exists for t greater than 0 and the function is 0 for t less than 0. So here the value is from 0 to infinity. So write 0 to infinity x of tau h of t minus tau d tau. But here the system is non-causal. So for that, the limits of the integral will changes to minus infinity to t h of tau into x of t minus tau d tau. Okay. Next, the third one. If a non-causal signal is applied to a causal system, non-causal. So it has to go for a negative and a positives. Okay. Now, so it is negatives and as well as positives up to t, whatever the value of t. Hence, the x of t is from minus infinity to t. Okay. And it's a causal system. System is causal system. So we have to go for 0 to infinity, because the system is causal. So the impulse response of the system is h of tau. That is a causal. We have to only get the positive values. Hence, we have to go for 0 to infinity. And the last one, if a causal signal is applied to a causal system, both are causals. That means system is causal and the signal is causal. That means we have to get the positive values only. We have to get the positive values for both signal and system. So hence we can write integral 0 to t t, 0 to t, up to which point we have? 0 to t, h of tau, x of t minus tau d tau, or integral 0 to t, x of tau, h of t minus tau d tau. Because both are causal, hence we have to go for positive, that is greater than 0 to t. Here also 0 to t. Simple. The first one is the general formula. General formula. As both the signal and system both are non-causal, so I applied the formula, and the response y of t equal to the convolution of h of t and x of t is nothing but integral minus infinity h of tau x of t minus tau d tau, or integral minus infinity x of tau h of t minus tau d tau. We can represent in any way. The second one is signal is causal, that will be applied to a system which is non-causal. Causal signal is applied to a non-causal system. Non-causal system. So the system is non-causal. Hence the response y of t equal to integral minus infinity to t minus infinity to t h of tau x of t minus tau d tau. Because here the system is non-causal. Non-causal. Hence we have to take the limits as minus infinity to t. And signal is causal. Signal is causal. So consider this one, x of tau. That means causal. So we have to go for 0 to infinity. 0 to infinity. If a non-causal signal is applied to a causal system, here the system is causal. System is causal. So I consider from 0 to infinity h of tau, x of t minus tau d tau. That is the response y of t equal to. And the y of t equal to system is causal and the signal is non-causal. Hence I have taken minus infinity to t. The limits minus infinity to t, x of tau, h of t minus tau, d tau. So these are the formulas for this thing. These are the formulas for this thing. Both are same. Hence these both are also same. And the last one, if a causal signal is applied to a causal system, both are causal, means integral y of t, the response y of t equal to 0 to t, h of tau, x of t minus tau, d tau. That will be equal to integral 0 to t, x of tau, h of t minus tau, d tau, or h of tau, x of t minus tau, d tau. Whatever it may, both are same. So here the remembrance of this one and this one are easy, because here both are non-causal, so the limits are from minus infinity to plus infinity. Here both are causal, so the limits are between 0 to t. So whenever the signal exists in that part, that is only for positive part, because both are causal means positive part. So 0 to t. So the condition is this case and this case. So I had given a procedure how to remember. Simple. Whenever they said it is a causal signal, so at x of tau we have to write 0 to infinity, and non-causal means minus infinity to t. In the same way, causal system, so we have to write at h of tau we have to write 0 to infinity, and non-causal signal, that means at the signal we have to write minus infinity to t. In this way you can easily remember these two, and the first and last one are easy to remember. So these are the four ways of getting the response of a system. So when different signals are given to the different types of systems, how can you find out the response? Means we can find out the response in these four ways. Okay, so this is a combination of causal and non-causals applied to causal and non-causal systems. Causal and non-causal signals applied to causal and non-causal systems. Okay, so these are four different combinations for getting the response of this system. So this is the explanation about response of the linear system. Okay, now I will go for the summary of today's class. Now I will go for the summary of today's class. What I explained in this class. Summary. First, I started a fresh unit, that is analysis of linear systems. I had gone for the introduction. Introduction of. So in the introduction, I explained you about the system. Okay, and linear time invariant system, linear time variant systems. Okay, after that I explained you about linear system. After that I explained you about impulse response, and last I explained you about the response of a linear system. So in this class I explained, start with the introduction of analysis of linear systems, and then I have given what a system is, and then what a linear time invariant, outline what a linear time invariant and linear time variant, and then I want to explain you about linear system, and then impulse response. I explained the concept of impulse response, and at the last I explained the topic response of a linear system. This is what I explained in this class. With this I am finishing today's class. Thank you one and all.